Welcome to this explainer. We use computers literally every single day to work, play, and connect. But have you ever stopped to think about how the abstract words we type into a screen actually turn into real physical action? Today, we're taking a journey to the center of the machine.
Seriously, how does a line of code actually flip a physical switch? It's the core mystery of what we call the computer abstraction hierarchy. On the surface, we're writing human-readable code, it's logical, it's safe, and it's easy to read. But deep down, the machine is just a hunk of physical hardware, silicon, microscopic wires, and electricity. So how on earth do we bridge that massive gap between an abstract idea in software and a physical electrical charge in the hardware? Let's figure it out. Here's our roadmap for the explainer today. First, we'll look at code-to-machine translation, then the instruction set architecture, the central processing unit, the arithmetic logic unit, and finally, memory and program execution. Let's dive right in.
Starting off with Section 1, Code-to-Machine Translation.
This is the very top layer of our abstraction hierarchy. It's where humans and computers first, shake hands. Let's look at the contrast between high-level and low-level programming languages. When you're writing in a high-level language, think Python or Snap, you're using massive abstractions. You don't have to stress about where your data physically lives. The language just handles it with garbage collection, automatically managing and freeing up memory for you. But if you drop down to a low-level language like C, you completely lose those safety nets. You get direct control over the hardware, absolutely, but you have to manually manage your memory. And if you forget to free up a memory block, boom, you've got a memory bug. So high-level gives you that safety and speed of development, while low-level gives you unparalleled control and raw efficiency.
But here's the catch. Whether it's high or low, the computer's hardware still doesn't understand it. It needs machine code. And that's where our two main translators step in, compilers and interpreters. A compiler takes your entire source code and translates the whole shebang all at once into a machine language program or object code. Once that translation is done, it is incredibly fast to execute. An interpreter, on the flip side, translates and executes your code line by line, on the fly. This makes debugging so much easier because you can just pause and tweak things midstream. In the real world, professional developers will often use an interpreter to debug their code quickly, and then hit it with a compiler to create that final lightning-fast application.
Moving right along to Section 2, Instruction Set Architecture.
Okay, so we've translated our code into ones and zeros, but how does the physical hardware actually know what those ones and zeros mean? The answer is the ISA, the Instruction Set Architecture. You can think of the ISA as a binding contract between the software and the hardware. It clearly defines the specific vocabulary of acceptable instructions and operands that a given processor understands. When you compile code, you're compiling it for a specific ISA, like x86 for most desktop PCs or ARM for the smartphone in your pocket. Basically, if a CPU implements an ISA, it promises to run all the software written for it.
Now, what's really fascinating here is the critical distinction between the ISA and the microarchitecture. People mix these up all the time, but they serve entirely different purposes. The ISA is just the external language front end. It's just the interface contract. The microarchitecture, however, is the internal physical blueprint back end. This means you can have two completely different CPUs designed by completely separate teams, like Intel Skylake and AMD Zen, with entirely different internal physical wiring. But because they both support the x86 ISA, they can run the exact same software. Pretty wild, right?
Let's step down another layer to Section 3, the Central Processing Unit. We've passed through the software translations and those architectural contracts, now resuming right into the physical brain of the computer itself, the CPU. And inside the CPU, the control unit is the absolute boss. It literally acts as the traffic controller of the whole system. It reads the translated instructions, decodes them so it understands the required microoperations, and then tightly coordinates the flow of data between all the different parts of the processor. It makes absolutely sure everything happens in the exact right sequence with perfect synchronization to avoid any messy data collisions. So how does this play out in real time? It runs on what's called the fetch, decode, execute cycle. This is the ticking heartbeat of the machine, driven by the system clock. With every single tick, the control unit fetches an instruction from memory. Then it decodes that instruction to figure out what actually needs to be done. And finally, it executes the operation. Fetch, decode, execute. Over and over again, literally billions of times per second.
That brings us to Section 4, the Arithmetic Logic Unit.
Right in the middle of that execution phase, All the actual math happens in the ALU, the beating heart of the CPU. Now, the ALU is built entirely out of fundamental logic gates. We're talking about microscopic electronic circuits that perform basic binary logic rules, AND, OR, XOR, and NOT. By combining these super simple gates, the ALU can pull off complex mathematical calculations. And here's a fun fact for you. How do you think the ALU knows if two numbers are equal? It actually doesn't have an equality circuit. Instead, it uses those logic gates to subtract one number from the other. If the mathematical result is exactly 0, the ALU flags them as equal. It's a brilliant little workaround.
Let's look at how this builds into something you rely on every single day, a bitwise AND operation. When your computer needs to figure out its IP network identity to connect to the internet, it takes your IP address and your subnet mask, and it compares them using a bitwise AND. It literally pushes these binary numbers through 32 microscopic AND gates operating in parallel. And only when both input bits are a 1 does a 1 actually pass through to the result. That microscopic instantaneous logic calculation is the exact thing keeping your device connected to the web right now.
But to make all of this dynamic, the ALU relies on multiplexers. Multiplexers abstract these logic gates even further. You can picture them as microscopic railroad switches. Based entirely on electrical control lines, a multiplexer selects exactly which inputs get to proceed to the output. It routes the data through the right logic gates at the exact right time, perfectly coordinated by that control unit we were just talking about.
And finally, we arrive at Section 5, Memory and Program Execution.
Okay, so we've seen the logic, but where does all this data actually live before and after processing, and how does it move around? Well, it lives in your system's memory, mapped logically into process image segments. See, when you run a program, your operating system doesn't just dump it randomly into RAM. It logically separates it out. It creates a text segment for your executable code. This gets read and execute permissions so you don't accidentally overwrite your own instructions. Then it maps out a totally separate data segment for your variables and values, which can be read and written to. This logical separation is absolutely vital for keeping your system stable.
But if we peel back that logical map, what is memory physically? At the end of the day, RAM is fundamentally just a massive matrix of microscopic capacitors. And a capacitor just stores an electrical charge. If there is a physical electrical charge trapped in that capacitor, the computer reads it as a binary 1. If it's discharged, it's a 0. And that's it. All your code, your photos, your games, your entire operating system, they are literally just massive patterns of trapped electrical charges. And to bring this whole system together, we have buses. Buses are parallel electrical conductors, literally just microscopic wires that bridge the CPU and the RAM. When that system clock ticks, these parallel wires physically carry those electrical charges straight from the RAM capacitors right into the CPU's registers, feeding the ALU's logic gates. So, a 64-bit bus? That's just 64 parallel wires carrying 64 electrical charges all at once, rushing back and forth, powering absolutely everything you do on a computer. We have built incredible high-level programming languages that make technology so accessible, smoothly abstracting away the memory management, the logic gates, and those tiny electrical charges. But here is the big question. Will the future of computing push abstractions so high that we completely lose touch with the physical magic of the hardware? Do we risk forgetting how the logic gates underneath it all actually work? It's definitely something to think about the next time you write a line of code or launch an app. You now know the complete journey from a high-level human idea all the way down to a microscopic capacitor. Thanks for joining me for this explainer, and keep questioning the technology you use every single day.